Hi guys, Justin here from chemistrynotes.com, and this is our video number 2 for section 11. Okay, section 11 is solutions. So this is our second video. The first video we introduced the things like molarity, molality, mass percent. What else do we have? Mole fraction and normality. And we did a sample problem where we had to calculate mass percent and molality, right? And today's video is all about the 3 factors that affect the solubility of a solution. So these are going to be things that affect how soluble a solute is in a solvent. Remember, the solute is what gets dissolved, and the solvent, usually water, is what does the dissolving. So let's get started. All right, the top of page 1 of our notes here for section 11, video number 2. 3 factors affecting the solubility of a solution. Number 1, structure effects. We may have heard the term like dissolves like, but essentially what that means is if something is polar, a polar solvent will dissolve it. If something is nonpolar, a nonpolar solvent will dissolve it. Famous polar solvents are water. The most common nonpolar solvent I can think of right now is hexane. So, structure effects. First bullet point. Solubility is favored when the solute and the solvent have similar polarities. I got 3 bullet points here. First one, polar solutes dissolve in polar solvents. Nonpolar solutes dissolve in nonpolar solvents. Some examples, vitamins A, D, E, and K, these are fat-soluble vitamins, right? And vitamins B and C are water-soluble. So vitamins B and C are going to have a lot of polar properties to them, whereas vitamins A, D, E, and K are going to be they're going to have a lot of nonpolar functional groups or attributes, or maybe even lack of functional groups if they're nonpolar. All right, number 2 takes much longer to explain than number 1. 1 was simple, structure effects. Number 2 is pressure effects. So this only affects gas solubility in a solvent. If you think about it, liquids and solids are already fairly compressed. So pressure really only has a dramatic effect on gases. So this only affects gas solubility in a solvent. For example, carbonation, CO2 gas in a bottle of soda. To ensure a large amount of CO2 being dissolved in the water that makes up a soda pop, the soda is bottled, and it's pressurized, right? It's bottled under high pressures, much higher than atmospheric pressure, because we want to, for lack of a better term, jam as much CO2 into the solution as a dissolved solute, right? So that's why the CO2 is bottled at high pressures. Now, the fizzing that happens when you open a can of Coke or when you twist off the lid of a bottle of Coke, the fizzing that occurs, that's CO2 molecules escaping from the liquid solvent, water, because they're no longer soluble at the much lower pressure, that pressure being 1 atmosphere pressure, right? Out here in the environment, it's essentially 1 atmosphere pressure. All right, so there is a law that discusses this. This is called Henry's law. Put a star by it. I've double underlined it. And Henry's law says the following. It says the amount of gas or vapor dissolved in a solution is proportional to the pressure of the gas above the solution. So the amount of gas dissolved in the solution is proportional to the pressure of the gas above the solution. Just picture my hands, right? I'm pushing down on that gas, pressurizing it, and dissolving as much gas into the bottle of Coke or into the container or into the scuba tank, etc. So Henry's law is C equals Kp. K is some constant, its value is not important. C is the concentration of dissolved gas, and P is the partial pressure of the gas solute above the solution. So I'm going to draw a sketch for you here, And what you see in the dark outline is basically a piston that can go up or down. So I've got situation 1, and I have another drawing where we have gas vapor in a sealed container. On top or above its liquid. So as in number 2, I've increased the pressure, haven't I? If I've increased the pressure, you see how the dark piston has moved down? What happens? Well, I'm going to get more vapor molecules or vapor particles dissolved in the liquid. You see how the liquid has more solute molecules dissolved in number 2? If I increase the pressure even more, like in the drawing for number 3, you can see the piston has moved even further down because I'm applying pressure and I'm dissolving even more gas solute. All right, so that's just a visual of some of the notes we've been taking, and that's then again that would be for a solution. So we're trying to get as much solute, gas solute, dissolved in our solvent. So that's pressure effects. It only has to concern with gases. Number 3, temperature effects. Got a brand new page of notes here to start temperature effects. Temperature effects, and we're going to talk about these in aqueous solutions only. And we are going to consider the solubilities of solids, liquids, and gas solutes separately. So when I say solid, liquid, and gas, I'm talking about them being solutes. These are the substances being dissolved in water. Water, our solvent. So a solid solute is an example, sugar, right? If you have hot tea versus iced tea, right? It's much easier to dissolve the sugar in hot tea as opposed to iced tea. And the same thing would be true with liquids. We'll see that. In a solid solute, example, sugar. Most solids become more soluble as temperature increases, like the hot tea and the iced tea example. B, liquid solute, for example, ethanol, right? If you ever have an alcoholic beverage, you have ethanol, drinking alcohol, dissolved in water, right? Well, most liquids become more soluble as temperature increases. So the liquids and solids they follow each other in suit. Higher the temperature, the easier it is, or the greater the solubility of that liquid and solid solute. Gases misbehave. They are the other way around, okay? Gases, if you increase the temperature of a solution, what do? Well, gas molecules have more kinetic energy, and then they're capable of escaping into the vapor phase. So what that means is most gas solutes become less soluble as the temperature increases. Now, I just kind of said a little bit about that out loud, but why is this? Well, at the top of this page of notes, we'll write the answer for that. How come gas solutes are less soluble as temperature increases? Well, because as the temperature of the solution increases, right, as temperature goes up, dissolved gas particles, and these can be gas molecules if it's like CO2, it can be gaseous atoms if you have an atom dissolved, but because as the temperature of the solution increases, dissolved gas particles have a greater tendency to escape the liquid, thus decreasing their solubility. Okay? Decreasing their solubility in the solvent. Now, what does that mean, greater tendency? Well, let's elaborate a little bit about what I've written there when I said greater tendency. So let's reread the top part. Because as the temperature of the solution increases, dissolved gas particles have a greater tendency to escape the liquid, thus decreasing their solubility in the solvent. Greater tendency, well, because there's more kinetic energy now. If I increase the temperature, I increase the kinetic energy because kinetic energy and temperature are directly related, and that's why gas particles are less soluble at higher temperatures in water. All right, so that's it for the second video from section 7. Section 7 is kind of like chapter 7, solutions and their properties. And the next video will be video number 3 on section 7, and we're going to cover vapor pressure of solutions. It's a big topic, so stick around for that.